Now, we also said actually, we didn't discuss much on that. These structures are called MSE walls, mechanically stable earth walls in the US. Okay. One advantage, of course, in that MSE wall method circulated by NHAI, National Highway Institute, is that they do a lot of short courses on the subject. They also have a lot of detailed guidelines for construction, for specifications, for you can say checking the designs also, what the contractor should do, what that member faculty or expert should certify actually. Even detail they have given now. No, that much detail is not there in this code, though it is a code of practice now. Even inside, I was just reading also again. It is a general guidance, definitely, no doubt on that. And it is based upon experience of the UK and construct such walls now. And the other thing was in the NHI, that is American method now, we are following the LRFD method. Here we are following the ultimate limit state method. About that, we have seen enough of it. So when we are starting to understand these things now, one important factor which you have seen already in the last class was that there is one factor which is introduced. It's a factor called Fn. F means partial factor, say partial factor basically, and this is subtitled subscript as Fn. Now these are very small letters, so you should see the soft copy and then remember these values also. Remember this terminology. This is Fn. So what we are looking at is we are looking at Fn, this value, and this factor should be applied to take into account the ramifications of failure of the structure. So what did we see last time was that when we got to construct abutments, structures directly supporting waterways, trunk and principal roads or railways, or inhabited buildings, dams, sea walls, and slopes, river draining walls and slopes now. In all these cases, it is category 3, that is high ramification. What is my ramification now? The result is going to be a loss of men and property. That is loss of life and property. That is the main thing now. Whereas when you go to, let us say, class 1 now, wherein the category is low, retaining walls and slopes less than 1.5 meter height. Now, obviously, if such wall falls, the damage is not going to be so much now. So we are not worried about that. That's what it says. Would result in minimal damage and loss of access. That is the main thing which you are considering when you have low factor actually. So the partial factor is going to be 1 only. In the second category, embankments and structures where failure would result in moderate damage and loss of services. Here there is minimal loss and moderate now. And there also the factor is 1 only. It's only 1.1 for all these cases we just seen actually. The main thing which you have to remember is this factor will apply to all other factors already. That means everything, if you let us say under partial factor set 1.5, if coming to class 3, category 3, we are going to apply 1.5 to 1.1. So obviously, every factor like this is going to increase now. So we have to be very careful how to select this category 3. And for that, they have given basically a lot of visual examples. One is the category 1, which we said already, minimal damage now. A noise barrier. Noise barrier obviously means that we are not going to put any structure here now. On the top now, there is no structure, no road really on that now. It's just a barrier. And then a simple retaining wall of maximum height 1.5 or a new or reinstated slope, but then it is very, very, very shallow kind of slope actually. And that means the angle is going to be maybe around 30 degrees or so. Definitely well less than 45 degrees. So obviously, a damage to these things is not going to be cause any loss of property and things like this. Then category 2 also factor is 1 only, but then important road, let us say like this now. So what is trying to be said is that if this line which you are going to draw, that means from the foundation level upward actually, 45 degrees. So if it is within the edge only, then we're not worried. Like the railway line also, they are trying to say 1:1, you are going to draw a line, then the damage is going to be of category 2 only. Like this for every kind of structure, they are given in great detail actually. So that visually we understand where is category 2 is going to come now. And also foundations now, when this distance between a house and the, I can say the bund or embankment is going to be definitely much more than H. H is the height of this now. Then also we're not worried actually. And also when we got these voids which are really there, when you got these voids, cavernous voids in limestone and things like this, so we're not so much worried. It also comes under category 2. And obviously, also in all these cases, is a non-principal road, not very important road. For example, probably we can say that the village roads are non-principal roads now. Even MDR could be important road. So very less important roads can be embankments could be considered like this. Then category 3. Yes, if it is cutting into the pavement, if this line is going to cut into the pavement now, and also even outside you are going to draw this line actually, then it's going to be almost touching this. And like this, if this line at the edge of the building and draw to this now is 1:1. So in all the cases, in the railways case, or when water storage ponds are there now, in all these cases, particularly abutments, obviously, it is going to be critical. So in all these cases now, we are going to take that category 3, and category 3 means obviously the factor is going to be 1.1. Factor of FN ramification failure is going to be 1.1. Like this, they have illustrated foundations also in many different ways. Earlier we said category 1 when the distance is more than H now, and now between the building and this embankment, if the distance is less than H, less than the height of this embankment, naturally this is going to be critical. It's going to be category 3. And so they have defined now what are the main things which are going to be there. Earlier we said this category is only 1, but now we are going to have railway line over that now. Obviously, that is going to be important, and it's going to be taken as category 3. And again, if this failure plane, H1 failure plane is going to be passing through this now, and passing the center of that now, naturally it is critical. So like this, they are given very clear description of what is going to be considered. The factor of ramification, category 3. And where we don't have to consider also is given very clearly. Then we have got partial material factor for reinforcements. So the partial factor is actually FM, F sub M. So FM is categorized into 4 categories basically, called FM1 and FM2, and FM1 again under 2 heads, FM11 and FM12 and FM21, FM22. If you see the logic of this is very interesting. FM11 means actually refers to the intended purpose, manufacture to cover the possible reductions in the capacity of the material as a whole, compare the characteristic value deduced from the control test specimens, and possible inaccuracy in the assessment of the resistance of the structural element resulting from modeling errors. So they are talking of modeling errors actually. Okay, you remember we have mentioned we are going to do the index testing for weight, width, and tensile strength, isn't it? And obviously that value is going to be used for the entire design. Basically, that means we are going to use such long and wide materials, and we are still based upon only 200 millimeter wide sample. So there is a modeling error when you are extending this strength actually to wider samples in the field. Naturally, that is going to be there. There is also a case when we are going to extrapolate the rest data. Extrapolation means, creep is there. For creep now, we are considering creep for 120 years. We have seen that last class. Now, we are not going to test for 120 years, obviously. We are going to do some extrapolation in terms of temperature change using the polymeric behavior and all. We will get into that when you go through the long-term design strength, how to evaluate it. And so what we are going to do, we are probably going to do for in log cycle now, 1 hour to 10 hours, 10 hours, 100 hours, 100 hours, 1000 hours. So we may do up to say 1000 hours or 10,000 hours and extend it beyond for years, basically. So the extension extrapolation test data. And we have not test data to verify also. And that too we are going to do by short-term method of changing temperature itself, not really. So all these things are going to be causing extrapolation of test data. So that means extrapolation of 1 log cycle. Supposing you have done for 1 year, we are extending to 2. We are extending to 10 years. That is, 1 log cycle. Okay. And if you got data for 10 years, extend 100 years now. So that extrapolation, we are doing real extrapolation now. Naturally, we are going to be quite serious about that now. So we got these 2 factors. Then damage accessibility, then environment now. So all of them are going to multiply it by 1 by 1. I mean, FM1 is equal to FM11 into FM12. And same way, FM2 also is going to be FM21 into FM22. And again, we are going to multiply. So remember that now, if you are just going to have 1.5, let us say one of this now, we are going to multiply all of them together. So it becomes a huge number basically. And that is why we have to be quite careful. So if you understand this particular picture here now, small picture, what is really done in this case is that we got the allowable strength, let us say in this case of considering all of them now, T is ultimate strength. That means the value which you are going to get of tensile strength in the laboratory, and that divided by Fm, I mean multiplication of all these factors, and obviously also the ramification failure if it's going to be under the category 3, and that is going to give us the design strength, let us say. And for the design strength now, you can easily see that the design strength usually could be just 50% of the actual ultimate value. So all these factors have to be evaluated very thoroughly, correctly, then only we'll get a meaningful lesson. So I will skip these things. We'll see how to work around all of them now. And then, of course, we have the material factors, interaction, that means friction. So what did we say? There could be two different ways of friction being generated. One is that the soil or reinforcement bond where potential failure surface crosses a layer of reinforcement. The soil reinforcement interaction mechanism in this case is one of pull-out resistance. What is happening now? We thought that it is a small model I have shown you earlier also. This small model of our reinforced wall now. So this is a assumed failure plane. Let us say 45 plus 5 by 2. And then if this wedge is going to come out now, if this triangular wedge is going to come out now, naturally there will be attempted pull out now. So that is what we call as potential surface crosses reinforcement is from here to here now. Okay, and it's being pulled out. This whole wedge is going to come, so it will be pulled out. That means this much is pulled out. This is part of it. So this pulling out effect is what we are going to do, and sometimes we call it as a bond also. And so the test we are going to do is a pull-out test in a tank. That means we take a tank, fill the soil to half now, place our reinforcement, and place the soil here again, and then of course apply normal stresses. For the range of normal stresses we are going to have in the field, naturally we are going to apply the tension here, I mean pull out here, and then get the bond friction. Bond friction really means that dividing whatever value you got by the actual value of 5 which you are going to get now. So that is the pull-out resistance, you can call it now. The other parameter is going to be soil reinforcement bond where the potential surface coincides a layer of reinforcement. That means, for example, if this entire thing is going to be moving out, that means if this entire wall, top half of the wall is going to move out, naturally there is a friction generated at the entire space, or at the entire space here, or at the base. Basically, it occurs to the base now. So in this case, the top portion is all going to come out now. So friction is generated at the interface of the geosynthetic and the soil now. That is the area we are going to look at now. So in this case, it is sliding resistance now, because the entire thing is acting as one pedaler piece, and that is done by a modified air-shear kind of test now. So the pull-out kind of thing is done in a special test apparatus, and the sliding is going to be done in a modified air-shear box. So these two are going to be, both are required in order to be able to take into account the actual pull-out from the wedge now and sliding resistance along a layer, complete layer now. So these are the factors which are going to apply, and we will see in later course what is the factors now. Then there are factors which are meant to also be load factors. So load factor can be for the self-weight of the soil, that is self-weight of the soil, and then any external dead loads now, and then of course external live loads now. So obviously for the design, we are going to multiply that value, whatever load factor, partial load factor we are going to have, by the load actually. So the design load is going to be this actual load, okay, and there is characteristic disturbing load now, and the design load is going to be multiplying that factor by this now. Usually all the factors which are considering are going to be greater than 1. Then the other novel situation they have developed also is they have developed, unlike any other methodology, they developed 3 load combinations. Load combination A, load combination B, load combination C, considering the overall stability of the structure. So if you see this now, this entire thing is going to be a mass. That means there are reinforcements within this body, and also there is a select fill soil in this now. And at the moment we are assuming that it is like a free body. The whole wall actually, reinforced soil wall, is going to act like a free body. We'll see again more detail later. So the point is that, so that is one body with reinforcement, and there is a sloping surcharge on this now, and then there could be a UDL kind of thing on this now. So, and of course there is a pressure here now. There will be also bearing capacity and things like this. So what is we are going to do is, in the combination A now, every load we are going to increase by 1.5, 1.5, 1.5, 1.5, 1.5. You can see that everything is increased. That is the load factor we are going to have as 1.5 for walls. We'll see some minor change could be there for abutments. And again, the combination B is We'll see why we are going to use a combination, why we are going to use combination B, we'll see. But in this combination now, we'll find that the self weight of the reinforced soil mass is taken only as actual weight, and then whatever sloping surcharge we are going to have, that also we are going to actual sloping surcharge, and then of course this UDL kind of thing. Earlier, it was there on the embankment or on the slope itself partially and extending beyond also. So we are not going to consider that part of it. We are going to consider only the portion of the load UDL outside this entire reinforced mass. So that is again 1.5. So that is one combination B. In the combination C, yes, everything is factor is only one now. There is no incremental factor of safety. So then what is it we are trying to achieve with this is, if you just look at the combination A, this combination considers the maximum values of all loads and therefore normally generates maximum reinforcement tension and foundation bearing pressure. It's going to give you the maximum reinforcement tension and foundation bearing pressure. It might also determine the reinforcement requirement to satisfy the pullout. Sometimes pullout also could be critical. But otherwise, it's going to actually always give you the maximum reinforcement tension and bearing pressure. That means vertical load which is going to act upon the foundation. Okay. Pullout is actually normally governed by the combination B, but we can also see sometimes this also comes under combination A. So we have to check this also. Then combination B is, we have seen already, this combination considers a maximum overturning load. We have seen that, if you just go back now, we've seen that here the actual values only are there, actual loads are there, only this earth pressure only is increased. And the combination considers maximum overturning loads together with the minimum of self-mass of structure and superimposed traffic load. Okay, this combination normally dictates the reinforcement requirement for pull-out and is normally the worst case for sliding along the base. Now, what is happening in this case is, if you recall, this point we have to remember also, that if you consider there is a layer of reinforcement, let us say, there is a layer of reinforcement. Just assume this now. Isn't it? I mean, I'm not able to draw perfectly, but let's say it's a line, single line now. Now we have seen that either the bond or sliding is going to occur on this now, depending upon where it is placed now, depending upon how the failure plane is going to cut this. But anyway, that's going to act along this plane. So whatever is the angle now, assume that is a delta. Normally phi is the value of angle of intersection or shear resistance. So that is tan phi is the soil to soil value, and delta is the what you call the parameter which you are going to use, abbreviation you are going to use for the interface friction now. So always, the actual thing is going to be, we are going to essentially use sandy soils now. So what is friction we can generate right now? It will be sigma tan phi. Sigma is vertical stress now. Tan phi means in this case phi is equal to delta. Interface is going to be delta angle. So we are going to think of sigma tan delta as the frictional force which is going to act upon this now. Okay, act along this now. So when once you're taking no further coefficient or no further load factor now, so which means it's going to give minimum value of sigma tan delta. On this side now, if you consider the same thing now, we are actually increasing the load by 1.5 times. That means we are going to have sigma more. So it's normally going to be safe. That's why it says actually. Okay. So that is what is going to happen in this case. Maximum turning moment, overturning moment, and a minimal support system now. Okay. So that is what is going to happen. In the third case, there is a factor of partial factor is going to be 1 only for all the 3 loadings. So what did we say now? Combination B is going to really critical for pull-out resistance. Okay, we had checked, but then definitely the worst case for sliding. But anyway there. So pull-out sometimes is mostly it is combination B only, but rarely it could be combination A also. We had checked for both of them, that means. Okay, in combination C, we are only considering the actual dead loads without any partial load factors. So this combination, when you should use now? We should use obviously serviceability limit statements. We are going for settlement. Settlement is caused by actual loads only, not assumed loads. Okay, the self weight and that part of live load is which is going to act permanently on the system is what we are going to have for settlement. So that is why combination C is not having any factors at all. Actual loads which are going to be there are used. Remember this now. This is one, this is one, this is one also. Okay. So that is only meant for essentially settlement. What we mean is that is serviceability limit state. Okay. And so we think of foundation settlements now as well as generating reinforcement tensions for checking serviceability limit state. So at serviceability limit state now, we can also see what is the reinforcement tension which is actually generated now. Earlier we got hypothetical values because increased loads and things like that made it overcritical. Now at this case now, we can actually find out what is the actual tension mobilized. We can just check with this now. Okay. So that is combination A, B, C. So for all these designs which are going to do, for all the walls we are going to do, wall or abutment what we are going to do, we are always going to work with combination A, combination B, combination C. So that goes without saying now. And this is what I mentioned. There are cases when we are going to take all of them, A, B, C. Mass of the reinforced cell body, mass of the backfill on top of the reinforced cell body, earth pressure behind the cell body. So whatever we have considered actually, they have given a table now, and also the vehicle traffic, how to do also is mentioned basically, how we are going to take UDL also, the standard value for this. In India also we have a standard values for this at least, okay. We call as regular surcharge basically. So apart from this factors now, we have to have these UDLs for design now. And in our country, it's actually 24 kVA we use basically. Okay. So the point is that whatever I have shown you in the combination ABC in the pictures, that is exactly same thing is given a table now for walls, associated walls now. What about abutments now? Now, what is the difference between wall and abutment now? Essentially, on wall now, we are assuming that it's going to be accurate pressure. And an abutment, we are assuming that the pressure will be K naught, but we'll see rather when you go further, we'll see what is the kind of thing we are going to have. So here, obviously, the combination ABC we have given, they are only marginally different from the earlier ones now. So in design abutment, we look into these factors. So what are factors I have shown you, ABC, was for walls actually in the pictures. And we had to follow this table to be able to design an abutment, a bridge abutment particularly. And then the load factors are already given you. Okay, extended loads are already discussed. Extended level loads are discussed now. What about the soil material factors? So soil also is a material only. So it is now the substitute is FMS. Is the material factor safety for soil actually. And what do we apply on tan phi? And tan phi, tan phi dash P means it is going to be peak values. So tan phi prime P is the peak values. And are we going to apply any factor now? No, it's only one only. To be applied to C prime, effective cohesion. FMS in this case is 1.6, and in this case is going to be, that means in the saturation state it's going to be 1 only. So we are going to apply factor of 1.6 actually, whereas for the case of phi, we are going to, for the case of tan phi prime peak, we are going to apply no factor. Okay, undrained cohesion we are going to do sometimes. If you are looking at immediate stability of the wall actually in place, so clay foundations particularly, the factor is going to be 1 only, unity only. Then reinforcement factors, as I already mentioned, that will be FM is the final value, and we said FM11 into FM12 into FM21 into FM22, all of them are going to be multiplied, and that is already described now. And what about the interface factor now? So that is going to be the factor for the sliding is going to 1.3. For ultimate limit state, serviceable limit state is only 1. And pull-out resistance, obviously, in this case 1.3. That means the coefficient is exactly same for both. And here also, it is the same for both sliding and pull-out now. So for serviceability limit, it is same. Okay. Then what about bearing capacity? So bearing capacity, we are applying to Q ultimate. Okay, Q ultimate, the metal factor safety we are considering in this case is 1.35. And for sliding along the base sliding we are talking of, earlier we talked of sliding along the reinforcements actually. Here the base sliding, the entire wall is going to move. And further the factor is only 1.2. Now this is where we differ actually. That means foundation bearing capacity to apply to Q ultimate. So long as they follow the British code, it's fine. But in India, we know that we are going to use factors of equivalent to 2.5 and 3 actually. So we have to be quite cautious in trying to pick up these values. Of course, in this case, we are going to use these values only because very rarely this is a problem. Very rarely is a problem. So it doesn't really matter what we are going to use because the width is going to be very large actually. And you know, for sands, the width of the foundation is going to be very important basically. And so it doesn't really matter because even if you put 2.5 also, it is still going to be within the limits of the bearing capacity. Okay, so we got these summary factors which are really there now. So what did we do? We had load factors and load combinations, and we had metal factor of safety for angle of intersection phi and C, and then for reinforcement, for the interface values, and also for the bearing capacity and for the sliding now. So these are going to set the parameters for us to do the design basically. So what is the procedure we are going to use now? They are going to flow chart now. Now it's difficult for you to read everything now. First is what we call as sizing. That means we are going to prescribe what is the size of the mass. We will just come to that now. After that, we are going to do what we call as extensibility analysis. Extensibility analysis first thing now. Okay. And after doing this now, we are going through. Remember, for sizing, we are not bothered with anything else. We are not bothered. We are bothered with total structure only. What is the length and height and everything else we are going to see. And then getting that size of the mass, which are going to be what we call a reinforced soil mass, we are going to have the extensibility check now. After that, most important is we are going to select the type of reinforcement. That means after we are sure that what is happening, that means stable and external conditions now, we are going to select the reinforcement type. That means is it a grid, is it a geotextile, is it a strap, is it a metallic strap axis strip? All of them we are going to pick up because the calculations are going to depend upon those things. Then we go through internal stability. So that means we are going to select the type of reinforcement. So in internal stability assessment now, what is it we are going to do? We are going to get the what is the required strength of the material. We are going to get the required spacing of the material. We are going to get also the vertical spacing and horizontal spacing if it is going to be stiff kind of thing. If it is a sheet kind of thing like a geotextile and geogrid now, it is may occupy the entire wall actually. Okay. So all these things are decided when once you know the type of the reinforcement and when once you get the internal assessment made, internal stability made, we are going to get what is the actual strength of the material required. Okay. We are also going to get what is the length of reinforcement required. That means first you satisfied the total length requirement for the external stability. That is the first check we are going to do for internal stability. If that is not sufficient, then we have to extend the reinforced length also. That means from external stability length, we may have to increase the length also, but we can't decrease the length anyway. Okay, that is one thing is there. For doing this, we got two methods, which you are going to see. We are not going to look at this. We are going to look at what we call as the tie-back wedge method and coherent gravity method. There are two basic methods, which we will see also as we keep going. Mainly, the coherent gravity method is for a metallic reinforcement, what we call as inextensible reinforcement. In today's practice, we are going to consider the geotextiles and the geogrids and the geostraps, that means all bottom materials, as extensible material. So the tie-back wedge method, which we are going to use, is meant for common geosynthetics we are going to use for common cases now. And for metallic reinforcement, what we mean is that they are inextensible. Okay, I am adding that word. I mean, I am emphasizing the inextensible word because earlier even the polymeric strip was considered by some as inextensible. So the polymeric strip and metallic strap are going to both considered as a coherent gravity. But today we are classifying the geosynthetic strap also as extensible. Now it comes under tie-back wedge method only. But it is not enough now. When you got complicated loading, we do design by tie-back wedge method and also check by the coherent gravity method. So coherent gravity method is a must for metallic reinforcement and cross check for complicated loadings. Okay. So from this now we get all the data. And then of course we are going to see how to specify the materials at the end of the day, how to specify and all. We are going to do that now, and that gives the design now. So basically it starts with initial sizing, then go to extensibility, then select the type now, then do the internal stability to get the length and breadth of the material and the strength of the material required, either by the tie-back wedge method or by the coherent gravity method, which depends on the type of reinforcement essentially. So that is the flow chart which we are going to think now. So what is the first step we are going to have? The first step is what is the nominal reinforcement length we are going to have. Length means per length per the face. Face of the wall is going to be the concrete panel, let us say. So from that, how much is the length which you are going to use now? What is the initial trial length? The trial length, initial trial length in this method is 0.7 h. We'll see what is that h really means. We can say h is height now. What height we are going to see? And what we mean is that now we also have minimum 3 meters now. So the initial trial length is going to be 0.7 h. And then if this is not sufficient for some reasons, either external or internal stability, we are going to increase it now. Just to repeat again, if h is equal to 10 meters, initial length of the reinforcement is going to be 7 meters. And with a prerequisite that the minimum length is going to be 3 meters. I can also add that there is a French code which gives me the length of the reinforcement, minimum length of the reinforcement as 2.5 meters also. So you can say the range is between 2.5 to 3. So in the British code, we use 3 meters as the length of reinforcement required. Minimum length, that is called, we can call as a trial length now. For a bridge reinforcement, the greater of 0.6 h plus 2 or 7 meters. So we can see this now. If the height is 10 meters, let us say, for bridge abutment, so that will be 6 meters plus 2, 8 meters. So either 8 meters or 7 meters means naturally we are going to pick up the greater one. And so in this case, it is only height 0.7 h, that is normal. Here we are going to pick up the higher of the two values. Then for other kind of walls, we'll see what other kind of walls, not without walls and things that we've seen yesterday. And for all of them now, in the top half, we are going to have a length of 0.7 h. In the bottom half, we can have 0.4 h now. Why? The trapezoid wall means, at the bottom, we are going to have less length because of the hilly nature, and we can't have that much length now. And so the minimum length required at the bottom was 0.4 h. And at the top of the structure, it's going to 0.7 h now. So minimum length of 0.4 h is going to be in the bottom 3 meter side of the wall. So again, stepped walls are going to be, again, top stepped wall means, like tires. One tire or the other, second and third tire now. And in that case, it's going to be 0.7 h is the top half of the structure. Okay, so like this, we are going to have minimum prescriptions to start with now. And the same thing is given here also, except that other conditions, for the trapezoidal wall and other things are also mentioned here now. So earlier we have drafted that, but this, more often than not, we are trying to give you the exact page of the code such that no confusion arises from you. For you, we can check up these values again and again, because when you retype it, there could be some mistakes also. So that's why most of the pictures or most equations are taken from the original soft copy. So this is what we have to say very clearly. What is it we are trying to say? We thought of normal simple wall, there's no problem at all. Height is height. Now in this case now, what is it we are going to have? Height is going to be the height above the foundation. That's anyway clear. And then in this case, we're going to sloping such. Okay. You are going to draw a line actually, which is tan inverse 0.3. So this line is going to be drawn. Wherever this line is going to meet the side slope of the embankment at the top, that means slope now. So from that level now. So that becomes the design height now. The actual height is going to be H1 only, but design height is going to be H. We should remember that now. Okay. In this case also, in the case of a bridge abutment now, wherein the this real abutment, in the case that the deck slab is going to rest on the seat, bridge seat, and this is the wall now. This is the real abutment. So in this case, the height is going to be from the base to the top layer here. So that is H now. And again, the same values for a full kind of embankment on the top of the wall now. We'll follow the same system. And so the height is going to be, what I'm trying to say is more than the actual height which you see. And here also, we are going to follow the same rules. So for each one of them now, we got clear indications of what is the design height. Okay. So that is the height now. So once you got that, for other case also, it is mentioned clearly how to pick up this height, because that is starting point for us now. Okay, so the design height is going to be obviously h, and the actual height could be subscript of h1 and things like this now. For simplification, I think they use the terminology h is the design height now. So assuming the design height as h now, okay, for a given case, and if it is a wall now, what is the length of reinforcement? Length of reinforcement is going to be 0.7 h. That is what is mentioned here now. Okay, so that is the initial trial length now. And we can take it as a continuous mass, let us say, and take unit length of that now. That is what we are always designing. Like in normal design also, we design like per running meter, we say. So we are going to do for in unit length, let us say. Now for our analysis now, of course, a plane stress condition like a regulated wall, the point we are trying to make is this is a reinforced soil mass. So what is it there now? We got all the reinforcement within the body. We don't know still what is the size and everything else, spacing, nothing we know. But we know that we are going to reinforce it. And so it's going to act like a single composite mass now. So what is it we are trying to look at is, in this mass, what is it we know? As of now, we didn't place a reinforcement, but reinforcement is going to be light only. It will be definitely lighter than the soil itself, the fill material. But then we would have had a selected soil in this case. To begin with, let us say we are going to pick up sand. We are going to pick up coarse sand. Just assume that now. If you are going to coarse sand, conduct a compaction test now and find out the so-called OMC and MDD. And so we are going to use MDD value of that now. And if we know that the height is h now, so all of them we can find out what is the total weight of this mass now. Okay, we know the shape now, we can find out the total weight of the, or total mass, I should say mass, total mass of this entire thing now. So now this entire thing is assumed as a free body. What do free body means? The whole thing is going to move this way, that way, overturn, horizontally, laterally, anything it can move. So it's a free body now. So it is an analysis of the free body which you are going to do, and without initially bothering about the presence of the reinforcement within the body. So the whole body can slide, let us say. The whole body can overturn. Okay, these are two things now. The whole body is going to give load, the bearing pressure on the bottom of foundation. So the three things are going to do for the so-called ascent stability. What is going to happen now? It may slide along the base now, it may overturn also, and then it is going to apply a load on the foundation. Foundation in this case means initially soil only. So the advantage of all of them is going to be this will not require normally on a reasonably good soil, no special foundation required, unlike a regular concrete retaining wall now. That is the advantage and essence of the entire work which you are going to do. So anyway, so this is what we call as ascent stability as a reinforced soil mass. So all of them are being given in different ways. We'll come into these details as we keep going now. Then of course comes to the foundation part of it. We have to again choose the minimum foundation depth for this entire thing now, because we'll start constructing the wall as well that now. So assume that the foundation is going to be of this kind of thing. Okay, we are going to, if this is the kind of slope we are going to have, that slope outside the wall basically, and we are going to take that 1 meter away and then draw a horizontal line, and then we know the depth of this now, which we are going to find, that is called dm. So this dm, the minimum embedment for beta s is equal to 0. That means beta is equal to 0 means that means it's horizontal here. Okay, and what is that now? It is h over 20 for walls, and it will h over 10 for abutment. That means if your height is going to be 10 meters, okay, so 10 by 20, 0.5 meters is going to be coming out for that, and naturally it's 1 meter for abutments now. So that is how it's defined, and we can define it also as function of the resistance and things like that. But anyway, it's easy for us to understand this now. So if this angle is going to be 18 degrees, so then we again take for walls, that means if it's going to be side slope like this now, it's going to be h over 10, like angle being 0 for abutments now, and for beta is equal to 27 degrees, it's going to be h by 7. If it is much more steeper, it's going to be much more height now. So the embedment depth, the minimum embedment depth is defined by this code clearly, and that is what we're going to start. It will vary from h by 5 to h by 20, h by 20 for normal walls and normal horizontal this one. So normally this is a service road, then we're not worried. But if it is a slope like this now, naturally the values will be, the values of dm is going to be more, the depth of embedment is going to be more, and we do not want to go more, because if this entire depth is going to more now, the wall has to start from that level now. It's not only portion above, it is portion below also we are going to have the wall. That means we are going to have all the reinforcements, which is going to make it expensive. So the abutment depth is going to be taken as the minimum abutment depth based on the code. Okay, we'll just close after a few minutes. The other thing most important is what I call a differential sketch in this entire code now. Remember that we are going to deal with three kinds of soils in the same wall design. One, of course, is very obvious. It is the foundation soil. Foundation not our choice, basically. So we are interested in finding out, obviously, what are three things now? We're interested in finding out the effective parameters. We have to find out the C prime, phi prime, and effective gamma for this soil, foundation soil. Then this soil here now is going to cause earth pressure on this wall. Okay, so this is a natural soil. In the case of a bridge abutment approach now, naturally it's also filled up soil, but then it could be natural soil. It could be also the same soil which are using for filling the back of the wall now. Okay, and if it is a different soil, which is gas pressure to us now, so again we are going to have, earlier we said C1, phi 1 and gamma 1. Here we are going to say C2, phi 2 and gamma 2, and earth pressure given by that is K2. Okay, and then soil 1, of course, is soil which is selected by us for making the wall now, because it becomes reinforced soil mass. We want it to be in general free draining. We wanted to have good friction, because once the soil has good friction and good density, it is going to give you good resistance for sliding and the bond also. So this is a select soil, you can say, like I've shown you in the earlier patents, old patents now. So again, we are going to think of the values of C, phi, everything else in the same way. And as I said, in some cases like bridge approach now, these two soils could be same only. It could be different also, but it could be also same. But anyway, we are going to again effective angle of shear resistance, and we got effective cohesion intercept, and we got effective unit weight, and then pressure arising out of it now. Okay. So all of them we should remember clearly that there are always going to be three kinds of soils. And when we speak on this, we'll say earth pressure here now. The earth pressure here obviously is given by this now. When you talk of stresses within the body, naturally it is going to be given by this now. When you are going to talk of the pressure here on the vertical load or vertical stress on the due to this wall on the foundation, let us see what is the story actually. Okay, so we should remember these values now. So like this, we got H, and actual height of the structure is H1. H1 or something is there. I'm unable to read myself also. So this is actual height of the wall now. Okay, so all this angle we are going to talk of this now. We already talked of this angle here also, which is beta now. This is of course tan inverse of 0.3. We are going for defining the height for design. So all of them are going to be important. So mind you, this picture makes it clear also. When we talk about the height of the wall now, we are talking about the foundational level now, because this is abutment basically. Okay, so this is foundation area. So starting from the bottom of the foundation and going up to the entire wall height, and then also going up further, defined by this line, which is tan inverse 0.3. So that's why the H is going to be the increased height because of the sloping surcharge we call now, the actual height of the wall now above the ground level, and the depth of embedment, that is foundation depth, is what we're going to think of. All of them combined together will give us the design height now. So that means if you are just to repeat the same thing in different words now, if the height of the wall above the ground level, if the ground level was here, if you are considering the height of the wall above the ground level, for example, it could be 10 meters. But then because we got a sloping surcharge now, we are going to add up this portion. Because we have foundation, we're going to add up this now. So the 10 meters actually is not going to be 10 meters for design. It may be say 10 plus 1 meter and another 10 plus 1 meter here. So it may be 12 meter. So design height for all our calculations is going to be both considering the top of the wall and also the foundation. So this is going to give us the actual height and the three soils now. What is the next indication for us is we are going to do three things. We will now next class. So we are going to talk of the bearing and tilt failure. We are going to talk of forward sliding, and we are going to talk of overall global stability. Now this of course we don't do ourselves. We can always use software for this now. Essentially we are going to talk about the bearing. That means the bearing capacity kind of thing, and any different statements are going to occur, and the rotation is going to occur because of the tilt actually. Okay, and then the forward sliding essentially at the base. So these are the considerations for extensibility. So again, I'll repeat now. We got a design height H, we got design height H, and then we also got initial trial length as 0.7 H for a regular wall now. So that is reinforced soil mass, which is going to move straight at the base, or bearing and tilt failure, or of course overall global failure. All of them are occurring as though it is a single body, is a free body. That is important for us now. So within the body, nothing is happening. I mean, whatever is happening within the body, we're not considering that. Okay. So then, of course, we'll see how these first two aspects are going to take care of. Third one is essentially by software. We try to do it now. We realize that it's going to be important. But then for classwork now, we are going to do the bearing and tilt failure and the forward sliding. Okay. So as we keep going now, what is it we are going to do? We are going to essentially look at the first method of design, that is dryback wedge method, as an illustration. And because the core and gravity method is essentially used for metallic reinforcement, I'm going to invite one expert from the reinforcement company, Terry Army, to help us in teaching us what is the core and gravity method and what is the differences. I will also say some differences, but in actual practice, the Terry Army is expert in that now. And Mr. Atun Adhikari, who was my student long ago, and so he is expert in designs actually. He's got very good command on the subject also. So he will give us actually on 15th, when I finish all of them, all these initial portions, and also the LTDS kind of thing, then he will come over and give one lecture on the design. That will be on February 15th actually. Okay, fine then, thank you.